Okay, we're ready to start now. So the first one, question 1. Ordinary helium-neon laser light has a wavelength of 632.8 nanometers. What is the speed in air in meters per second? What is the speed in frequency in hertz? And what is its energy in joules? Okay, so let's start with A. What is the speed in air in meters per second? Okay, so this is helium-neon light which emits a red light, and the speed of that red light in air is the same as the speed of light. So here the answer to this, the speed or velocity v is equal to 3 times 10 to the 8th meters per second. Okay? So that was the expected answer here. All colors travel at the same speed, the speed of light. Yes? Yes. So let's see, in air, yes, because this is the speed of light in vacuum, okay? So if you divided that by 1.0003, you would get, a more accurate answer, right? Either way, we can do this, or we can say that V is equal to C over the index of refraction of air, and it's going to be 3 times 10 to the 8th meters per second over 1.00. How many zeros, Adam? 3 zeros. Yeah. So obviously if you do that, it's going to be a number slightly smaller than 3 times 10 to the 8th. But either one of the two is correct. Okay? So let's go to B. What is the its frequency in hertz? Okay, so frequency is the letter nu. So I need to find a relationship now that relates nu to what I am given, which is wavelength, lambda. Okay, so you open up your book. Can you find a formula that will give me nu with respect to lambda? Nu is equal to c, the speed of light, over lambda. Okay? So here you're going to say that nu is 3 times 10 to the 8th meters per second divided by lambda, which is 632.8 nanometers. Okay? And then nu is equal to 3 times 10 to the 8th meters per second over 632.8 times, nano is 10 to the negative 9 meters. Okay? So let's do the division here. Okay? Someone do this division for me. 3 times 10 to the 8th over 632.8 times 10 to the negative 9 on your calculator. 474 times 10 to the 12, because this 10 to the negative will go up on the numerator and become positive. Now, look at the units here. You have to be careful with the units, okay? It's meter over seconds, and here's meter over 1, okay? So what you do, you have meters over second times the inverse of that, 1 over m. Okay? And then let's see if I can get fancy here and change my colors. Then this meter with that meter cancel out. Okay? And then the answer is going to be 474 times 10 to the 12. 1 over second, okay, is a hertz. 1 over second is the definition of hertz. So it's 474 times 10 to the 12 hertz, or we can write it as 474. If I use now a metric prefix, what's 10 to the 12? Terahertz. Okay? So that's the answer to B. You can leave it either to this point or to that. If I ask you to give the answer in terahertz, give it in terahertz. If not, you can do it in one or the other form. And the next question is, what is its energy in joules? Okay? So let's continue to the next page. The energy. You need to find a formula for energy. Okay, if you look in your book, there must be a formula for energy of the different colors of light, and it's H times nu. Okay? So H is a constant, which is given, and I'll give you that on the test, Boltzmann's constant. Nu here is the frequency. We just found the frequency earlier, didn't we? Okay, so the energy is going to be H, which is 6.625 times 10 to the negative 34 joules seconds times the frequency which we came up to. How much was it? 474 terahertz. Okay. Now, we do the calculations here. Let me just write the numbers. 6.625 times 10 to the negative 34 joules seconds times 474 times 10 to the 12. Now hertz, it's 1 over second. Okay? And now I'm going to get fancy again. I'm going to use a different color. This second with that second cancel out. So my answer is going to be in joules. And the answer is going to be this number multiplied by this number and in joules. So if you do that, someone give me the answer here. 3.14 times 10 to the negative 19 joules. Okay? So this is the energy. This is, let's write this down so you remember what this means. This is the energy of one photon of the helium-neon laser, because that's what the question was asking, huh? The helium-neon laser of wavelength lambda equal to how much was the wavelength? 632.8 nanometers. Okay, that's from the previous. Yeah, 632.8 nanometers. So that's what this number is here. This is how much energy you have in one photon of this light color. Very, very small amount, 3.14 times 10 to the negative 19th. Very, very, very small. So it's going to take many, many of these photons, billions and trillions of these photons, to really add up to some amount of energy. But this is what this formula gives you here. This is the energy of one photon, Boltzmann constant, and that's the frequency of that photon. Okay? Okay, let's move on to the next question. Question number 2. Sketch a picture of a sine wave showing wave displacement versus distance at a given time. On this sketch, show the wavelength, positive and negative displacement, show the wave amplitude. Okay, this is simple stuff, straight out of the book. So, sine wave displacement versus time. So this is displacement. And this is time. And then let me just change color here so that you can see what we're doing. So here's the wave. And then change another color. Now the wavelength. Show the wavelength. Positive and negative wave displacement. Show the wave amplitude. Okay? Distance at a given time. Versus distance. Okay, so I have this wrong here. This is distance at a given time. Okay? It's not time. It's distance at a given time. So, if this is distance, the horizontal axis, the wavelength is from this peak to that peak. This is the wavelength. Or from this trough to this trough. This is your wavelength. The wavelength is distance. It's measured in meters, or nanometers, or millimeters. Okay? So this horizontal axis has to be in distance. And then, that's A, part A, answer A of the question. Part B says, show a positive and negative wave displacement. Well, this wave, at any point from here to there, this is a positive displacement. Positive, 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 positive. So this is positive displacement. Okay. And then, if I use this color, from this point to that point, this is all negative displacement. Okay? All these points on the curve, this is negative. Displacement. This is part B of question. And C says, show the wave amplitude. Okay. This is this color. So the amplitude of the wave is the distance at any point from the horizontal axis. Okay, this is the amplitude. It's also the displacement from the resting position. So the amplitude changes continuously. That's what the curve shows. And at this point here you have the maximum positive, and at this point here you have the maximum negative amplitude. Okay? So this distance is the amplitude. And you measure it over here on the displacement axis. Okay? It changes continuously. So this is part C of the answer. So here's positive amplitude, and down here you have negative values for the amplitude. Okay. So that's question 2. Let's go to question 3. Sketch a picture of a sine wave showing wave displacement versus time at a given position. Okay? So, displacement versus time at a given position. Let me give you an example of this, physical example, so you understand. Remember we talked about the example of dropping a rock or something in a lake, and we'll create these waves that will be emanating from the center outward. Okay? Imagine now that you have a position that you're monitoring. Let's say this position right here. You have a buoy which is attached to the bottom of the ocean or the lake, and then you monitor that, you keep your eye on that position as time goes by. As these waves move outward, okay, from the center outward, when you keep your eye on this position, what do you think that buoy is going to do? Will go up and down, huh? Up and down. So in that position, because you have it tight, but it will be moving up and down. As time goes on, you're going to see it moving up, down, up, down. So if you plot that up and down, up and down, up and down, you're going to get this graph. You're going to get then displacement, how far it's going to go up or down from the reference position. And here, now it's going to be time at that position. Okay? And again, I'm going to change my colors. Now here's how your wave is going to look like. This is like the sine wave you saw on a scope in your electronics classes. It's displacement now versus time. Okay? And now that you have displacement versus time, if you measure from this point to that point, this is time now. Okay? From one peak to the next peak. This is now your period. Or if you measure from one trough to the other trough, this is now your period. Okay? So that's the answer to part A. B, show the wave amplitude. Well, the wave amplitude is in distance from the resting position. At this point, this is the amplitude. At this point in time, this is the amplitude. Okay, this vertical line. And you read it off from the displacement axis. This time, this is the amplitude here. So the amplitude changes, and you read it off right here on the left. This is the amplitude. That's part B. And then C says relate the period and frequency with a simple equation. And again, with optics, we use T for period and for frequency, which is inversely proportional. It's nu. Okay? Or nu is 1 over T. So those are your formulas when you deal with time. Question 4. Was that question 3? Did I miss 3 or no? It's 3. Okay, I didn't miss anything. Okay, question 4. Neodymium YAG laser has a wavelength of 1.064 micrometers. What is its equivalent wavelength in angstroms? Yeah, I mentioned that last time to you. So remember that we said that 1 angstrom is equal to 1.0 times 10 to the negative 10 meters. And then, therefore, 10 angstroms is 1 nanometer. Is that correct? Okay, so let's answer A. If the wavelength is 1.064 micrometers, that means this 1.064 times 10 to the negative 6 meters. So to convert it to angstroms, I need to make this 10 to the negative 10. So the way to do this would be this. Let's do this way, it will never fail you. Okay? 10 to the negative 6. So I need to multiply by 10 to the negative 4, so that minus 6 minus 4 will give me my minus 10. And then I also have to multiply by 10 to the plus 4. So multiplying by 10 to the negative 4 and 10 to the positive 4, I'm not changing my original number. That's meters, okay? So these two together now will give me 1.064 times 10 to the negative 10, which is angstroms, times 10 to the positive 4 meters. So I can multiply the 1.064 by 10 to the positive 4, which will move the decimal point 4 positions to the right. I will take that decimal point 1, 2, 3, 4. So that will give me 10640 times 10 to the negative 10 meters, or 10,640 angstroms. Is that correct? Because 10 to the negative 10 means 1 angstrom. So that's how you would do this. That's A. So let's do B. 1.064 have to do it right here. I don't have a free space. Let me do it right here with, yes.
When you converted it and you did the 10 to the negative 6 times 10 to the negative 4, 10 to the positive 4, yeah, all I did was just move the decimal point over 4. So going from negative 6 to negative 10. Is there a pitfall in my logic?
No.
I came up with the right answer. It's a waste of it. Am I going to get screwed someday by doing it that way?
Yes, you may run into the problem where you may, instead of going to the right, you go to the left. You may forget. You have to always check your answer at the end if it really makes sense. See?
But assuming you do that.
Yes. If you do that, yeah, I would do it that way. But I'm showing you here
Okay.
mathematically how you would do it to the nth detail,
Right.
so you make sure that you will never go wrong. Yeah. Yeah. If you are confident that you remember your powers of 10, then you can do it in a faster way. Okay, let's do B with a different color, nanometers. So here's where we started with. Lambda 1.064 micrometers. And we need to go to nanometers. Well, nanometers, you go from 0.64 times 10 to the negative 6 meters. I need to go to 10 to the negative 9. So to go to 10 to the negative 9, I'm going to take my 10 to the negative 6, multiply by 10 to the negative 3 to give me 10 to the negative 9, multiply also by 10 to the positive 3, so I don't change my number here. That's meters. Okay. Those two together will give me the 10 to the negative 9, which is a nano. And now I'm going to do this quickly. I multiply 10 to the positive 3 by this number, which will move in my decimal point 3 positions to the right, which is going to be 1064 10 to the negative 9 nanometers. Okay? So that's B. And then C, to give the answer in meters, okay? What do I need to do if I start from the previous answer here? Lambda now is 1064 times 10 to the negative 9 meters. I need to get rid of that 10 to the negative 9 and write it as meters. So what do I do now to the decimal point, which is right here? Need to move it to the left or to the right? Left. 9 positions to the left. Okay? So I'm going to change color here. Let's use this color here. See, the decimal point is right there. Now, let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then move the decimal point right there. Okay? So I'm going to fill all of those with zeros here. So it's going to be 0.0, 0, 0, 0, 0, 0, 0, 0. Oops. I'm sorry. I ran into my numbers there. I got carried away. Okay. So there's a zero right there. And then I have this 1, 0, 6, 4. And this is meters. Okay? Okay. So we got this done. Question 5. From the diagram of the electromagnetic spectrum, determine the wavelength spread in nanometers and frequency spread in hertz for visible light. Okay? So I have this on the next page. I'm going to go back and forth between these two pages. So let's do the wavelength first. So the wavelength, here's the visible light, which has been extracted from the big graph up on the top. So the wavelength is down here. So the wavelength of visible light spans from 0.7 times 10 to the negative 6, which is 0.7 micrometers, that's for red, to 0.4 micrometers for violet, this is red, or the one we prefer is 700 nanometers for red, and this is 400 nanometers for violet. Okay? So you need to know that. You need to memorize that. You need to know that if you go out and say that you have gone to school and you took a course in photonics. Okay? This is one of those things that someone expects you to remember. So if I go back now, question B. Identify the electromagnetic radiation that has wavelengths around 10 to the negative 12 meters and 10 to the 21st hertz in frequency. Okay, 10 to the negative 12 meters. You're going to come up here on this top waveform. And then let me change the color now. Let's use red. 10 to the negative 12. You see? It's right here. 10 to the negative 12. Right there. What does it say under it? Gamma rays. Okay? So, part B of the question for wavelengths of 10 to the negative 12 is gamma rays. Okay? Or the frequency, see down here, 10 to the 20th. This is 10 to the 22nd, so we're about 10 to the 21st right there. See, in that area? 10 to the 21st hertz. Gamma rays. Let's go back. The last question says, identify that, yes. This part? Yeah. 10 to the 21st. 5A? Oh, we haven't done that. Okay, yes, you're right. Let's do that. Well, frequencies, you look at the top of this chart here. So these are frequencies. So for red, is 4.3 times 10 to the 14th. Or, to write it in terahertz, that would be 10 to the 12th. And then you move the decimal point here to the right 2 places. That would give you 430 terahertz for red. And then over here for violet, to convert this to terahertz, this would be 10 to the 12th. So you have to move the decimal point here 2 positions to the right. I will give you 750 terahertz. So the spread, the frequency spread, is 430 terahertz for red through 750 terahertz for violet for the visible spectrum. Yes. And I think we were left with identify the electromagnetic radiation with a wavelength around 1 meter and frequency of 10 to the 8th hertz. So let's go to the diagram. Meter, okay, this is wavelength. Where's the wavelength? It's about 1 meter. Change colors. Let me change to blue. Here is 1 meter, right there. You see that? 1 meter. So if you come down here, it says TV and then microwave. They're kind of condensed in there. but 1 meter, the frequency, excuse me, UHF. Yeah, 1 meter is 300 megahertz. It's UHF. It's television. So you can do it this way. See, lambda is 1 meter. Okay. You can see from the graph here, it says it should be actually TV, not microwave. Microwave is much higher. But to find the frequency, mu is C over lambda. And if you do that, 3 times 10 to the 8th meters per second, and lambda is 1 meter, okay? So 3 times 10 to the 8th is the same as 300 times 10 to the 6th hertz, or 300 megahertz. 300 megahertz is UHF. And that's where the new band now for high definition television, digital television, that's where it's up there in the UHF. So the answer is television. Is that what it asks? It asks yeah, it's used for television. 300 megahertz. Okay. So we have answered up to question 5. So question 6 through 10 we'll do next time. So we're not going to have the test on Monday. We'll have it on Wednesday. Okay. So on Monday we'll finish up these questions, and give me 1 second here. Okay, give me 1 second here to tell you what